We are now going to talk about how we can use integrals to find the area between curves. For example, let's say I want to find the area between this function that I'm calling y equals f of x and the other function y equals g of x. Well, we could divide this region up into a bunch of little tiny rectangles and create a Riemann sum, just like how we first defined integrals. Each of these little tiny rectangles that I have drawn has a width that is a delta x, or dx, and they have a height that is the top function, which we called f of x, minus the bottom function, which we called g of x. So the area of one of these little rectangles would be the height, f minus g, times the width, delta x. That means the area of this total region would be the sum of the area of all of those little tiny rectangles. Essentially, we're creating a Riemann sum. And if we let delta x go to 0, if we increase the number of rectangles, so we have an infinite number of rectangles, then this is going to turn into an integral. And the thing that we're going to be integrating is the height of those rectangles, the top minus the bottom function, so f minus g, and we'll integrate that from x equal a, the left side of the object, to x equal b, the right side of the object. Now, it is possible that we may want to work sideways. In some cases, it's going to make more sense to chop our object up horizontally into a bunch of different rectangles. And we can find the area of each of these rectangles just by taking the length times the width. If we're slicing our object horizontally, the width of our little rectangles is actually going to be delta y, a change in y. So my width here is going to be a delta y. And the length of these rectangles is going to be the right side of the object minus the left side of the object. How I have this drawn, the right side would be x equal f of y, and the left side would be x equal g of y. So just like in the previous example, if we want to find the total area of this region, we would have to add up all of those little rectangles. We can apply the limit process and make that delta y go to 0, and this turns into an integral. We will be integrating the right side minus the left side with respect to y from the bottom of the object, y equals a, up to the top of the object, y equals b. All right, let's see how this works by doing some examples. Find the area between f of x equals x squared plus 3 and g of x equals the square root of x from x equal 1 to x equal 4. The first thing I'm going to do to solve this problem is draw a picture. Y equals x squared plus 3. The x squared tells me it's a parabola, and the plus 3 means it's been shifted up 3 units. Y equals the square root of x. That's my half of a sideways parabola. And I want to find the area between these curves from x equal 1 to x equal 3. So I've shaded in the region that we are interested in finding the area of. In this problem, it makes sense to slice this object vertically. So the width is going to be a delta x. The width of my rectangles is a delta x or a dx. And the height of each rectangle is going to be the top object minus the bottom. This means we're working in terms of x. So to set up my integral, I'm going to integrate the top object, x squared plus 3, minus the bottom, which is square root of x. And I'm going to integrate that from x equal 1 to x equal 4. We can do the integration. Let's see, antiderivative of x squared is x to the third over 3. Antiderivative of 3 is 3x. That square root of x, I'm going to rewrite that as x to the 1/2. To integrate, I add 1 to the power. I got x to the 3/2 divided by 3/2. Dividing by 3/2 is the same as multiplying by 2/3. So now my antiderivative is x to the third over 3 plus 3x minus 2/3 x to the 3/2. I have to evaluate this from 1 to 4. So I'm going to plug in x equal 4 into my antiderivative. Then I'll plug x equal 1 into my antiderivative and subtract those two quantities. I used a calculator to finish this problem, and I got 76 thirds. That would be the area between these curves. One thing to note is when you're integrating the top function minus the bottom function, that is giving you an area. You should always get a positive answer. If you get something that's negative, it means you made a mistake somewhere. Maybe you don't have the right bounds. Maybe you have the wrong function as the top function. All right, let's do another example. Find the area between f of x equals x squared and g of x equals 2x from x equals 0 to x equals 3. I'm going to start by graphing these functions by drawing a picture. Y equals x squared is a parabola. Y equals 2x is a line that goes through the origin. So I can see in my picture, I can visually tell these two functions intersect at the origin, but I can also see they have another intersection point as well. And so I want to figure out where these functions intersect. So I'm going to do that by using substitution. We have y equals x squared and y equals 2x, so I can just set those two functions equal to each other to figure out where they intersect. So when does x squared equals 2x? I'm going to set one side to 0 by subtracting the 2x. Then we have a common factor of x. We can take that x out, and we're left with an x minus 2. Setting each of my factors to 0 gives me x equals 0 and x equals 2. So these functions intersect at x equals 0, that's at the origin, and again at x equals 2. However, the region I care about goes from 0 to 3. So notice that these functions intersect in that region that I'm interested in. That means the function that's on the top changes at that point of intersection. So when I cut this region up, and again, I'm going to slice vertically. If I slice vertically, the width of my rectangles is a delta x or a dx. So I'll be working in terms of x. So if I slice this vertically, the top of the object on the left side is the line, but on the right side, when we're bigger than x equals 2, the top of the object is actually the parabola. So what this means is we're going to have to set up two integrals to solve this problem. When we go from x equals 0 to x equals 2, we're going to be integrating the top function, which is the line, 2x, minus the bottom function, which is the parabola, x squared. So we're going to have to integrate 2x minus x squared. Then we'll integrate from x equals 2 to x equals 3, so bounds from 2 to 3, and now the top function is the x squared, and the bottom function is the line or the 2x. So we're going to integrate x squared minus 2x. So I'm going to have to solve each of these integrals separately. That'll give me the area of those two separate regions, and then I'll add them together to get my final answer. So antiderivative of 2x would be 2x squared over 2 minus antiderivative of x squared, which is x to the third over 3. If I plug in my bounds of integration, when I plug 2 into that antiderivative, I end up getting 2 squared, which is 4, minus 2 to the third, which is 8, divided by 3. And then if we plug 0 in, we get 0. And so that simplifies down to 4 thirds. That's telling me the area of this region from x equals 0 to x equals 2 is 4 thirds. Then I do my second integral. Antiderivative of x squared is x to the third over 3. Antiderivative of 2x is x squared. Plugging in my bounds of integration, so I'm going to plug 3 into my antiderivative. I get 3 cubed divided by 3 minus 9. And then I plug 2 in. I got 8 thirds minus 4. I subtract those values, and that also gave me 4 thirds. So my final answer for this problem, I have to add the area of these two regions. 4 thirds plus 4 thirds gives me 8 thirds. Here's another example. Let's find the area between x equal y minus 1 squared and y equals x minus 1. Once again, I'm going to start by drawing a picture. x equal y minus 1 squared is a sideways parabola, but if you're not sure what that looks like, a great strategy is to make a table of values. Since this equation is solved for x, I'm going to pick a bunch of different numbers for y. So I just let y go from -2 to +2. We'll plug those values in and see what we get. If y is -2, -2 minus 1 is -3. -3 squared is 9. If y is -1, -1 minus 1 is -2. We square it, we get 4, etc. And then I went ahead and I plotted these points. I decided not to plot the point 9, -2, because that was just off the graph paper I had. So I started with the point 4, -1. So x is 4, y is -1. And then I plotted the point 1, 0, 0, 1, and 1, 2. And I can see that sideways parabola. The equation y equals x minus 1 is a line that has a y-intercept of -1 and a slope of 1, so up 1 over 1. And I can see that these two curves are intersecting at two places. It looks like on my graph they are intersecting at the point 1, 0, but there is another point of intersection up higher. So this is the region I want to find the area of, the area between these two curves. Now, if I want to slice vertically, I would have to write two integrals, because the object that's on the top, well, the object on the top is always the parabola, but the object on the bottom actually changes. On the left half, the bottom of the object is the parabola, and on the right half, the bottom is the line. So I'd have to set up two integrals if I wanted to slice vertically and work in terms of x. So instead, I'm going to slice this one horizontally. And if I slice horizontally, the right side of the object is always the line, and the left side of the object is always the parabola. If we want to slice this horizontally, that means the width of my rectangles is actually a delta y or a dy. That's telling me we're going to have to work in terms of y. And the length of these rectangles is going to be the right side minus the left side. So we're going to have to work in terms of y. We're going to take right minus left. That's the thing we're going to integrate. So first thing I'm going to do is I'm going to take my equations and make sure they're solved for x. I want my equations to be functions of y. So I'm going to take this line, y equals x minus 1, and I'm going to solve it for x. I can do that by just adding the 1, and I got x equal y plus 1. The second equation, this x equal y minus 1 squared, is already solved for x. So because I'm working in terms of y, both of my equations need to be solved for x. They need to be functions of y. All right, now I am ready to figure out where exactly do these two curves intersect. To do that, I'm going to set my equations equal to each other. We have the equation x equal y plus 1 and x equal y minus 1 squared. So I'm going to take y plus 1 and set that equal to y minus 1 squared. We're going to FOIL out the y minus 1 squared. That gave me y squared minus 2y plus 1. Then I'm going to set one side to 0. So I subtracted the y and subtracted the 1. That gave me 0 equals y squared minus 3y. I have a common factor of y. I pull out the y and I'm left with y minus 3. If I set both of my factors equal to 0, that gives me y equals 0 and y equal 3. So this bottom, this lower intersection point is at y equals 0, and the higher intersection point is at y equal 3. Finally, we are ready to set up our integral. We are going to integrate the right side of the object, which is my line, x equal y plus 1. So I'm going to take y plus 1 minus the left side of the object, which was x equal y minus 1 squared. So we're going to integrate line minus parabola, and our bounds of integration are going to be the bottom of the object, which is y equals 0, to the top of the object, which is y equals 3. One thing to notice is because we're working in terms of y, because we decided to slice horizontally and use the little dy, everything in our integral has to be a y, including our bounds of integration. So the 0 and 3, it's really important that those are y values as well. All right, let's finish this up by doing the integration. I went ahead and FOILed out the y minus 1 squared. We actually already did that earlier. It was y squared minus 2y plus 1. Then I distributed this negative and combined like terms. So that gave me a negative y squared. And then a plus 2y, which I added to that 1y. That gave me 3y. And then finally, I had a minus 1, which I added to the plus 1. That added up to 0. So I have to integrate negative y squared plus 3y from 0 to 3. My antiderivative is negative y to the third over 3 plus 3y squared over 2. I plugged in my bounds of integration, so I started by plugging in y equal 3. That gave me negative 27 over 3 plus 3 times 9 over 2. Plugged in 0, I got 0. Final answer was 9 halves. That would be the area between these curves. All right, that was my last example. As always, please let me know if you have any questions on this topic.